Alright, welcome everyone. So this is a problem about Minesweeper, kind of. So in this problem, you imagine that you have a chessboard where, okay, I need to pick two integers. Let's do like, freak. So M and N are both odd, yeah? No, that's not true. At least one of them is odd. No, sorry. Oh shit, what's the correct statement? At least one of them is even. So let's okay, let me just pick one. I'll just do this. I'm not gonna think too much about it. Yeah, you know what? This is a 3 by 6. Yeah, 2 5 is fine. And then there's a number written in some of the alternating cells. It's like, well, I don't know. Okay, let me do something that actually corresponds to some mines. All right, so for thematic reasons, we'll put like, how do you draw? Okay, I don't know how you draw Minesweeper mine. It's Minesweeper mine. Oh wow, the spikes are a lot smaller than I thought they were. Okay, we'll put like, we're gonna let red numbers denote mines, alright? So, actually no, I want to draw these differently so they look different. Although, it's really hard to draw multiple mines. Here, let's put one here. And then like, I don't know. Put like one here. And then there's like, okay, so you write a number corresponding to the number of mines. So here's a Minesweeper puzzle, alright? What? Oh shit, this is 2. This is 3. And you want to show in general there's a most fun solution. Over... Do I care that the integers are non-negative? I think I don't care about non-negative, because I could imagine shifting all the numbers by something. Is that true? Yeah, I feel like you can shift the numbers and like non-negative can't. If there's if I just increase all the numbers by like here. One, two, three, four, 5. Like imagine I have like 100 mines. If I take this picture. And then, you know, this is like 200, 400, 300, 400, 300, 300, 300, 300, 200, or whatever. Then I can shift all the numbers by like 200 or something. Imagine shifting all the numbers by 200 and it's like, okay, all I did was add 100 to each of these things. And then, you know, there's nothing special about 100. Like, if you're a little under 100, or a little more, okay. So I think, like, what this suggests is that I probably don't need the non-negative integer condition. Like I should just solve this as an integer system of equations. It's possible I need the integer condition. That I might believe, but I don't think I need the non-negative condition. Okay, so then because of that, what I can do is I can, if there's 2 different solutions, then I can subtract them and I can reduce to a picture where all of these are 0. Which I think is good. Like, I really, yeah, I mean, this is how linear algebra works. And now I have all zeros, and I want to show there's no way to do this such that, besides, again, allowing a negative number of mines, although not... Okay, actually, here's another thing. I claim I don't care about the integer condition. If I have a rational solution, I can scale that rational solution. And if I have a real solution, I can take a Hamel basis, like decompose R as a Q basis, as a Q vector space, and then take any Q component that's okay. So I don't care about that condition either, in fact. I only need to show that there's no real solution to the minesweeper puzzle, real, rational, whatever field you want out, honestly. Like so. Now, I do have a condition n+1, n+1, and that's because if I drop this condition, there's probably grids that do work, right? So, okay, let me pick an example of a grid that doesn't satisfy that, like say a 3x3 grid definitely doesn't have the property. And then if I checkerboard color it, there's ways to make this work, right? Like you can do 1 mine, -1 mine, 1 mine, -1. Right, so the claim is that if I have n+1, n+1 equals 1, then I should be able to force all the numbers to be 0. And that is some linear algebra condition. And I don't really want to... God. Okay. Why is it n+1, n+1 though? That feels... Like if I do... If I make m and n both, I don't know, 3 and 6. Like, are you telling me this one will have a non-trivial solution? I don't feel like this one really will either. I mean, okay, let's just try it and see what happens. So if I want to generate a non-trivial solution, I'm supposed to use something about the fact that this has a... I don't see how that's useful at all. Like what? I don't know. GCD... Oh shit, it's +1! Ah, crap. Sorry, I'm going the wrong way. Okay, honestly though, +1 I think makes it a little more... Like, I was looking at -1 and I was like, what the heck? Okay, we're gonna just wipe all of this. So if it's +1, then I guess it's like telling me I should try to extend the grid one more. And if I extend the grid one more, okay, so this is supposed to be some grid that has, right. So I can imagine that it's sort of like, okay, so let's pretend I extended the grid one more and do something like that or something. And then there's like some phantom green numbers or something, I don't know. I don't know what the green numbers are. Do I want to extend the grid this way or the other way? It shouldn't really matter. No, actually it might matter. Okay. I think this red number the red 0 doesn't help very much, so I'm gonna orient the grid the other way. We're gonna rotate everything. So I'm imagining I'm going to require that all of these numbers are 0. And then we have a requirement that like these are 0 or something. The Linalg, the numbers should form a basis. Yeah, no, I agree that's true. The claim is that if I, whatchamacallit? It would be it would be sufficient actually. Okay, I agree. It would be sufficient to show that if I change any particular green number to 1, then there exists a way to do it. Because then you get linear algebra magic. Because the number of variables is equal to the number of constraints. Which... is true. But I wonder if I can also do something like... you know the argument that goes, like, you take, like, the biggest number or whatever shit, and then try to blow something up. I guess that might not work very well here. But, like, I feel like most of the numbers have degree... I don't know. Yeah, we can see if the basis elements are, like, any good, I guess. Oh god, I really don't want to think about this. Ugh. This is just turning into UCMO 6. Yeah, I think we definitely expect this to be linear algebra in some way. I just don't see exactly... Like, I need to use this n+1 thing somehow. Why is it n+1 though? It's not Linalg. I think Linalg could give you some like, for example, I think the linear algebra tells you the intuition should be that you need to show not intuition, not even intuition. Like, the linear algebra does some things where, like, it shows me that it's enough to think about this situation where I have green zeros everywhere and I need to show the only solution is all red zeros. Why is the minesweeper putting the mines down? I think you should imagine you see a minesweeper puzzle and you need to prove that there's only, like... Yeah, okay, I agree we should change the wording to say that yeah, it's fine. Also, if 2, 5 doesn't work, I want to actually write down the example that doesn't work. I think that might help a little bit. So claim is that 2, 5 doesn't work, meaning I can get a non-trivial example. And actually, this is going to use the mod 3 thing. I guess that's kind of what I was trying to draw earlier. So let's see if I can draw this. 1, -1, 0, -1, 1. So the phantom 0 is kind of here. And I guess it's like 0. Zero. Okay, sorry. Wait, I should be... Wait, hang on. What? Sorry, the 0 is in the wrong place. Okay, so your claim is that you actually just know the eigenvalues of the matrix. Really? Okay, so you're taking let's see. Kronecker sum of two path matrices. Trick bashing combo is fun. When it works, yeah. Okay, actually, I want to draw more counterexamples, because I feel like I want to understand where this GCD condition is coming from, and I feel like something is up, because, you know, this... So, in general, let's pick, oh god. See, it's hard to draw big num. Let's do, like, let's do, 4 by 9. And see where the counterexample is, if there is one. Oh man, this highlight is completely in the wrong place. So the picture looks something like this, and then like, okay, what is the non-trivial example that's using my periodicity? So I probably start on the edge again, go -1, 1. Shit, no, this is wrong. Along the top, I need this to be... Ah, gosh. Ah, help! Everything's wrong. Ah! Okay, let's try that again. Okay, 0, 0. Oh my god. I bet, okay, does this look like it might work? Shit, but I can't have things here. -1, 1, -1, 1. And everything else 0. Is this a valid? No, this doesn't work. No. Actually, no, maybe this works. Does this work? I feel like this might work. Okay. Yeah, I think this works, and I think this is where all the counter. This is where the counter examples should come from. I have a. Oh, do I not have a? What does this line do? I have a ridge here, and then if I add more yellow highlights, here. Yeah, if I add more things that look like this, I can generate more counter examples. I've added something like that. Alright, let me figure out how to stitch these. Shit, I flipped the sign. No! Okay, yeah, so this is where the GCD condition gets used. Also, this figure is this picture is pretty bad. But here, these zeros are kind of the glue between the cells. And then there's just one unused. Okay, so I can generate as many counter examples as I want, right? Using this recipe. Yeah. Notably considering... I don't know if what this example does for me, though. Okay, anyways, yeah. Okay. Here's a different question. What is the... If I have a grid, and let's say, okay, so in the counter examples, there is, like, the first red number is, like, here, right? So it isn't unreasonable to say, let's say that... Cool, yeah, because I want to make sure the counter examples have the property that the whole, that there's stuff on the boundary, so that induction is, like, so let's say, like... Oh, God, I don't know whether to start in a corner. If I can show the corner is 0. Because in the counter example, hang on. Yeah, in the counter example, all the non-zero corners are filled. So there's a hope that if I can show that this number is 0, then there might be a way to, you know... Well, induction isn't going to preserve the GCD condition. Okay, why don't I just put a 1 here and see what happens? What problem are you working on? Oh yeah, this thing. I'll move it downwards. Where is a good way to place this? I don't know, man. Minesweeper. Yeah. What I've done, the only thing I've done so far is figure out the counter example if you don't have the GCD condition. Okay, so, frick. Can I do one of those, like, reflection things, actually? So, if I have a solution, then it's, like, various mirror images with respect to something, or I have to think exactly what that means. So, one of the... In any grid, in any valid grid, one of M and N is odd. So I should be able to, like, take a solution and add it to, like, a mirror image of some sort, and that should do something. I don't know what. Well, okay, what are the valid mirror images? So the valid grids are ones for which okay, so what's an example of a valid grid? So I need at least one of them to be even. So let's say that, you know, we have this as an even solution. Oh man, see, the thing is, like, for like literally even by even grid, like say I have like a 2x4. Does this have like any mirror symmetries that like... Oh dude, I have no idea. Okay, if I have mirror symmetry, like, if I have like a 3x4, so if one of the sides is odd, then there's a mirror symmetry where I can add something to its mirror image along this axis. And then I can assume it's symmetric around like something or other. Or even subtract them, maybe? I don't know, man. I don't know what if there's any symmetries I can use here. Dude, okay, I know how to do the problem for a 2 by n board. Right, if it's 2 by n, then, you know, you're happy because you can just... yeah, actually, so you can actually see the mod 3 right away. If it's 2 by n, then once you fill in a cell here, it goes like that. And then it's fine. And then, actually... Yeah, so a 2 by n board has a property that as soon as I fill in this cell, you can zigzag determine all of them. That's inspiring, and I think what that means is that in general, if I look on the... So at least one of them is even, right? So I would say maybe what we try is we say, okay, look at the thing that's even, and then fill in the red numbers, whatever they are, and then generate the rest of the table and see if we get stuck at the end. Right, is basically what's going to happen. I don't know how much I have faith in this strategy, but it is true that whatever the even thing is, if I call it, let's like a1, a2, up to am over 2, this should generate just everything else. In fact, actually, this entry is particularly good because this entry generates this minus am over 2. Okay, so I'm gonna... Do I want to pump the recursion? I mean, okay, it is some recursion, right? And then the question is, once I have a column, what happens after it? So the one that will go right after it is... Okay, so I need to do it from the... Oh, fuck. I should have put the... Okay, we're gonna put the A1 out under it. Because I actually don't want to write out the rest of the things on the bottom. But okay, there's some 0 in a corner, right? And then I write A1. And then this is minus A1. And then there's some 0 here. And this is A2. And then this is minus A1 plus A2. And then this is 0. This is A3. And this is minus A2 plus A3. And you keep going up until you reach the bottom. Let me just do up to like 5, and 5 can be like m. Alright. 0, 0. Okay, so we've changed to something, and now kind of at this point I can forget about this column or whatever, right? And then we get here, and basically the question is, if I imagine I keep doing this procedure, so then I generate a column, generate another column, generate another column, at what point do I get something that's like potentially bad? Meaning, wait, now I'm confused.
From the heat wave stole my emotions. I left my doubts when I was swept by the ocean, and every pulse from the tide was a finish line. A wave race we were made to ride. You and I were first in line, and we took their advice. I was with you.
So I wanted this map, like, the claim is that this map should be... You shouldn't be able to get all zeros, but I think that's just not... Hang on, something's wrong. Like, I feel like I'm composing the same matrix, and that's not good. Oh shit, I forgot about... Ah, crap. Okay, yeah. This one, okay. Sorry, the end behaves differently than the ones after it. Yeah. So I need to remember 2 rows of information, not just 1. Okay, well, that's not good for me. Okay, so... minus A1. This is A1 plus A2, right? And then this is A1 plus A2 plus A3. A2 plus... Wait, I feel like I've seen this particular thing sometime recently. Right. So the thing is, I want to I want to see when is it possible that I end up with. Okay, I'm just going to keep computing this for a while, because I want to see what happens. So here on the top, there's this behavior where it keeps What the hell is going on? This is not anything resembling 6. Like, I guess my question is, do I think I can eventually describe what's going on? I'm not 100%. I feel like I'm surprised because now this has like 4 things in it. Like, it feels like it's growing, which is really bad for me. I want it to be not growing. Maybe it's like a... Okay, I think at this point I'm curious what's gonna happen and I want to keep computing. Do I believe this though? Minus A3 is wrong. 3, 5, yeah, right. Minus 1, 2, 3. What the hell is going on? What kind of map is this? Like, the number of terms keeps changing on me, I feel like. I don't... Like, what... Like, I don't even know what the number of terms that's supposed to show up is. Maybe I should compute that first. It's like all ones. 1, 2, 2, 2, 2. 2, 3, 3, 3, 1. What the frick? 2, 2, 2, 2... 4, 3, 4, 2, 2... What? Am I doing this right? Wow, this is very disorienting. Should I be isolating the contribution? I guess that's equivalent. So where's A1 showing up? Like, A1 has showed up here, 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 and then it kind of... I mean, it goes down, which is, I guess, what we know in the counterexample, it just goes straight... wait, actually, what happens in the counterexample? In the counterexample, it's like there's a... It starts from the... In the counterexample, the entries of relevance are like this one and this one. So it's like... Oh, I don't have a middle zero here, because I picked the odd one. Well, actually, no. In the count... Wait, hang on. What the frick? That's really bad. In the counterexample, it's like -1, 1. Okay. Write all the white cells. This was one of the first things they did. So if you imagine there is a configuration for which there are 2 different solutions, then you subtract the 2 from each other, and it gives you a configuration where all the green numbers are 0. Yeah. Yeah. I agree it's nice, but also it's pretty standard in the sense I think I've done that particular subtraction on multiple different problems before. Like this is like the first thing you do in linear algebra, which is like if you have a system of equations and you want to check it as a unique solution or not, then first you see first you see what happens when it's all zero. So if you've ever taken this, like, if you ever try to use Cramer's rule or whatever, like you have a linear system of equations, you know, the case where the right hand sides are all equal to 0 is what tells you whether uniqueness holds. Okay, so anyways, I don't see what's going on with this. And the GCD condition I don't think is helping me. Do I want to use the... No, but I'm only promised... in the real in the situation where even... Yeah, I'm only promised there's an even side. I'm not promised there's an odd side. So I don't... Like, I kind of don't have much of a choice. Like, this has to be the first. Does it flip? Keep going. Okay, I'll go one more, but I don't see where this is going at all. Like, the extensions just keep getting longer. Honestly, I should come up with a better shorthand. This is so dense. A5, A2, A3, A4. Oh my god. This is a disaster. Oh no, this is a lot of... Hey, I mean, okay, on the bright side here, on the next column, I have like a -8 too. Oh god. Okay, I'm gonna adopt a shorter notation, alright, because this is getting so clunky I can't deal with it. I'm gonna stop writing the minus signs, and also I'm going to only write the indices. So, like 1, 2, 3, 4, 5 or whatever. Because I actually think the notation is starting to get in the way. So what we saw is we're going to start with the red numbers 1, 2, 3, 4, 5, and then, you know, here. And then this is 1, 2, 2, 3, 3, 4, 4, 5, 5, and then 1, 1, 2, 1, 2, 2, 1, 3, 1, 2, 3. 3, 2, 3, 4, 4, 3, 4, 5, 4, 5. I feel like that's already different than when I got here. Oh shit, I flipped the order. I flipped the order relative to the top. Okay, let me try it. Let me make it consistent with the top. Oh, this is so annoying. Oh my god, I'm so bad at this. Yeah. Die. 4 4 3 4 5 2 3 4 1 2 3 1 2, right? And then 2 1 2 3 1 2 3 4 2 3 4 5, and then so like it's not completely random, but the patterns aren't amazing. Okay, and then after that, 2 3 1 2 3 4 1 2 3 4 5 3 4 3. I feel like this is different from what I had above. Oh, I just fucked. There's a 3 here. Yeah. Yeah, okay. I think this compact notation is better. Right. And then this is 3. And then this is 2 3 4. This is 1 2 3 4 5. This is 1 2 3 4. This is 2 3. Uh 2 3. Okay, so do I believe that? What does the top row become after? I wish I picked a smaller example now, actually. Because I don't know what happens past here. I need to compute a while before I know what happens past the first like cycle. It flips? What does it mean it flips? Help. Shit. Okay, I should have done a smaller but 5 2 3 4. Is it 5 4? Oh, is that what happens? Oh my god, I can't compute this quickly enough. This is the claim, right? That eventually becomes 5 4 3 2 1. Oh god. Oh. 1 2 3. I mean, okay. Look at the middle two, it's symmetric. Oh, I see. I agree it's symmetric. Yeah, okay. Okay, so then what does that do? Like if I keep pushing the table, what happens? And then it starts repeating, right? So these are all empty. And then it's 5, 4, 3, 2, 1. So, you know, we have... Oops. I don't know what that did. Okay. Okay, I mean, yeah, I'm glad it repeats, but I don't see what to do with that information. Like, it means I can solve any small m or something, but... Like, I need some result that tells me that for... Okay, what was this? This was like... Let's say m is the odd one, alright? So let's say m is odd. Or, sorry, even. And then so this is like... This number here is like m halves. And I need to say that... Okay, so that's m even, this is m halves. And then this is like columns 1, 2, 3, n. And I need to, like, if n plus 1 is relatively prime to n plus 1, I need a condition that says, like, the resulting linear combination or whatever is, like, yeah. Like, it's good that it's symmetric, but what do you do with that? So, okay, when is the... This is column 2m plus 1, which matches what we... This is column 2m plus 1, which is what we kind of expect, and this is column 1. Wait, actually that's a really... Okay, wait, actually if they're all 0, that's pretty strong. Wait, if they're all 0... interesting. Okay. If they're all 0, does that mean there were... Like, if I only look at some of the m over 2 things... okay, well 5 is prime, so rip me, but... Wait, okay, yeah, so that's actually kind of surprising, because it means the counterexample... I found, like, some counterexamples, but actually the set of counterexamples is enormous. You can put any numbers you want in the leftmost column, and it'll resolve to a valid minesweeper thing at that cutoff. So, okay, that part is good, that it... Yeah, actually, in fact, I can give a pretty good description. Now that I know it actually vanishes up there, I really... Okay, I should have seen this earlier, maybe. But, like, if you pick a number, the set of places where it appears is exactly a parallelogram that looks like this. So it goes out and then sweeps back in the way you expect it to. It's like... Yeah. Okay, so actually it's... Okay. Now I feel a little stupid, because it's like, okay, that's actually just exactly the description. Like, I wrote out all these entries, But if I had actually looked at the contribution from each individual thing, it's literally a diamond thing. Okay, diamonds are rhombuses. This is not this is a parallelogram. That's fine. However, yeah, maybe I regret picking m equals 10 a little bit now, because 11 is prime, so I can't generate the earlier counterexamples easily. If I picked like m equals 8, then it might be a little easier to see why certain columns are counterexamples. But I feel like I should be able to also just run over the problem directly. Like, I can actually just more or less... Okay, so by symmetry, I should assume I'm in the left half of this picture, right? And then, in that case, the matrix is pretty easy to describe. Because if I'm in the left half of the picture... sorry. Or maybe it doesn't have that much. 3, let's see, 3's apex is... Okay, but I should definitely do some... Well, what are they called? Some column operation, right? Oh, I don't see it. This is on the right track, though. I think so. The fact that we got this all zero thing was really important. And now I just... How do I show that each of the matrices corresponding to each column is invertible? Help. Oh, actually, 5 is important. 5 literally, its appearances are just shoot straight up. So the contribution of the 5 doesn't do anything. We can kind of just ignore it. Does that help my analysis? I feel like that because I know that the true answer has to involve something about like the entire GCD thing, which is not good for me. But I like it feels if I had been told the answer was something else, I would be trying to induct now by deleting 5. But I don't think that's what I want to do. Anyone see what I should do next? Okay, so okay. 5 is, yeah. 5 is odd, which isn't, feels like it matters in this example. Alright. Why is it based on, like, really 2m plus 1? Or not, m plus 1, which is like 2 times m halves plus 1. Like, it's saying that the reason that these are all invertible has to do with the prime 11, which is not a prime I was expecting to show up. So I should be doing something with the extra row, right? Or something? Like, if I imagine, let's imagine I extend the row one more. Then, actually, I do like doing that because it makes the whole thing more symmetric. Like now your 5 has, yeah. Actually, it's better if I have this extra row, right? Because now everything's more symmetric. And something about 11. I don't see why the like, if 11 is prime, should I be looking at can I get the determinants to be non-zero mod 11? Is that a true statement or something? Is that what is that a statement I want? I want the determinants to not be 0 in certain columns that don't have a GCD issue. But, like, okay. What are the I want in column n. In column n, if n is not congruent to -1 mod m plus 1, then the determinant, I want this to imply the determinant isn't 0. So put another way, I want, if the determinant is 0, then also n plus 1 divides n plus 1. Okay, maybe I should just compute the determinants. I wonder if, like, the determinants will just, like, let's see. Okay, I'm actually going to compute some of the determinants now. So this identity matrix is determinant 1. The matrix after it is 1, 1, 2, 2, 3, 3, 4, 4, 4, 5. And if I how do you compute the determinant of this? It's also 1. This is determinant 1. It's lower triangular. That feels bad to me, though. I don't know, maybe it's fine. And then the one after it is 1, 2, 1, 2, 3, 2, 3, 4, 3, 4, 5, 4. Ah, God. No, I don't want to compute this. I have no idea, but okay. So this is a 1 here. So I should look at this this is 1 here, so I should look at this. This is 0. So up to some sign that I can't really do in my head because I'm too old for this, I think this one is also 1. I think these all have unit determinant. Okay. That's not good. I thought maybe there is a chance the determinant would, like, be some function of n and m that would... Yeah, I don't see it. Also, I totally lied. It's not... This... I wrote it with n plus 1, but that's just not true. Like, this is, this should be a co-prime condition. Which actually, by this column, by column 3, you could potentially fail, right? Okay, so this is all wrong. So I should take this determinant a little more seriously. Like, so this determinant could be 0 if m plus 1 happened to be divisible by... Wait, hang on. It's n... Oh, shit. Wait. This column could be 0? No. I refuse to believe that. In column 12 by 2, no, 10 by 2, 8 by 2. Did we find an example for 8 by 2? We did, right? How, I feel like this matrix is obviously upper hey, what the fuck's going on? Wait, we found a counterexample for 8 by 2, right? If you let this be 1, minus 1. What was the example? Wait, we had a counterexample for 8 by 2. What was it? One. What the fuck is going on? What am I doing? Wait, this is a counter example. This 1 minus 1. 0. What? No, it's not. 1. Wait. This is 4 by 2, not 8 by 2. Wait, so 8 by 2 would be if I had. Oh, fucking heck. Today's not my day. Okay, we agree there was a counterexample for this one, right? Where I do No, that's not correct. Oh god, I can't do anything right. Oh, I'm off by 1. The condition is supposed to be that the column after it is invertible, is all 0. Yeah, it's the column after it, not the column that. Okay. Okay, so in that case, why? Am I bad at counting? 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, this is 11. Wait, okay. When m equals 8 and n equals 2. What the fuck's going on? Right. Okay, yeah, 2m plus 1. Right. Okay. So I'm off by 1. You should look at. You're looking at whether the column after it is invertible, and then Okay, I don't know anymore. Okay, wait, but can I just use Euclidean algorithm then? Like, if I have an initial... Okay, imagine I have a column and then some column is like 0. Then... Also, I know that this column all the way out here is identically 0, no matter what this one was. So, I can... If I look at the period of the entire process... do you just get a Euclidean algorithm issue? I think that might just happen, right? I think that actually, the fact that this is all 0, I think, is actually really good for me because now I can, if I have another column that's all 0, then I can, I get some period. When I have columns that are all 0, I have a periodicity result. So because, like, if I imagined like there was some bad column, like if I imagine like there's some other bad 0 column, like, for example, the one that I was just talking about, like if in the case where it was divisible, if I have a bad column here, then there's a mirror image. Is that what happens after a bad column? Yeah, you get a mirror image and then there's another bad column here. And then similarly, there's another bad column here. And then now what you get is a counterexample past that, like against this green one. But now you get a contradiction to like induction or whatever. Because if I look at a minimal MN pair, then this process here will give me by division algorithm or whatever, it'll give me another bad thing. And I think that just solves the problem. That should actually just be the whole thing. Like because this green one happens to actually be all 0, if I have other columns that are all 0, then I can reduce down. And that's how I use the divisibility condition. I think that's it. Does that work? I think people realized that earlier now that I'm thinking about what was said in the chat. That's what's going on. I see. The fact that this green column is always 0 tells you if you have an orange column that's all 0, then you can reduce n. Yeah, okay. Alright, we did it. Yeah, I think that works. Actually, that's really surprising. No, that. I feel like I didn't properly appreciate the green column being 0. I was like, oh wow, it's 0, that's nice, and then didn't think too much about it. But that's actually the whole thing. Like, the reason the problem works so cleanly is because the column's always 0, so you can... This is gonna be... yeah. Actually, even freezing it, yeah, it's just, you should freeze it in terms of minimal period, right? And then whichever the first column that 0 is, just, it has to divide. Do you think of the green? Thank you for saying for first time chat. What is this Google presentation saying? I don't quite follow. Is this an induction or wait? Okay, so 0 I'm assuming is a minesweeper. Yeah, you're gonna have to explain this spreadsheet or from this presentation. I don't understand what this is saying. What am I looking at? Start from one corner that's labeled 0, okay. Okay, so you're saying the red numbers are equal, so the orange and yellow and green numbers are equal. That's fine. And then... what are the black squares after that? You get a cell that has to have 0 lines. Wait, what? In my thing here, you're claiming that this cell has 0 mines. Why is that true? Oh, I see. Okay. Yeah. Because this is 0. Okay, that's fine. Did I not? I feel like I should have run into this here. Okay, yeah, actually, that's this cell. Alright, this is 0 diagonal. So this cell has to have no mines. There, okay, that's the red one that I have here. Good. Then, now that this cell has 0 mines, then it tells you that this cell... Sorry, the red means that they sum to 0, right? And then so... you repeat that starting from the 0. Okay, and then you do the same thing, okay. Okay, so the black cell... Wait. Zero starting on the opposite side of the black cell. Hang on. So what, you're using like... this, if you know this one has no mines, then... the one above the black cell. And you also know this thing has no mines, so okay, I see. Then you're saying this thing, this thing, this thing. So this has no mines. And then it's a laser argument. Okay. Okay. Alright. Yeah, but this green one here is miraculous. And see, I wrote this with the odd case, but it should work even in the even situation, right? Like if I just imagine dropping all the... Right, but your laser thing is a thing assertion that the entire... okay. Yeah. Yeah, I think this period thing is also Just, yeah. Actually, I don't, yeah, it's fine even with the, okay, it doesn't matter. Okay, well, that is definitely going on the linear algebra unit. Alright, cool. Minesweeper. Is this problem original? AMC, oh no, it's too late. I'm not staying up till 1 for AMC. Kolmogorov, okay. Okay. Okay, well, anyways, that's that. For those of you on YouTube, thank you for tuning in. That was... how long did I spend on that? Okay, that could have been worse. Yeah, that's fine.